Okay, so I thought I would do a video going back over projectile motion. It's a vital part of Extension 1 HSC, and basically this video is going to go right back to the very beginning and walk you through every single thing you need to know for projectile motion. The first thing is just to understand the idea behind it is basically projecting something up. It's going to form some sort of parabolic nature, and it's going to eventually obviously come back down because of gravity. And we look at, okay, what's the angle it was projected at, what's the speed it was projected at, and with pieces of information we can find things like, well, what's the maximum height that this object will reach in the sky, or how many more meters ahead of me will it land. So this is the idea of projectile motion. So you can find out these pieces of information if you're given things like the angle it was projected at and the speed. So that's what you have here in this diagram to the left. And this is on your XY plane. So this is the nature that the curve produces. If you're just looking at your velocity line on its own with your angle there, we can represent the height of that velocity with v sine alpha, and that just goes back to your unit circle, and knowing that your horizontal distance will be v cos alpha, which makes sense because think about cos as adjacent over hypotenuse, etc. So what we can assume is that we can write the horizontal distance of the initial velocity as v cos alpha, and the vertical distance of the velocity as v sine alpha. So those are formulas you can assume. There's many formulas in projectile motion, and there's very few that you can assume. In other words, you don't have to prove the formula. However, there are a lot of formulas that you can't just memorize. You have to know how to prove that formula. And if you just memorize the formula, you're not going to get anywhere in the HSC. So these are two formulas you can assume. You do not have to prove these. What I'm going to do is write a list now of other formulas, including these two, that you can assume. So let's say that these are formulas we can assume. So you're not proving these. So straight away, it's our vertical and horizontal equations there for the velocity. What we can also assume is that when we're talking about horizontal projection, there's no forces acting on it, okay? So there's nothing affecting it, there's no acceleration there that is having any effect on it, unlike something vertical. So what we can assume is that your x double dot is 0. However, vertically we have what we call gravity. So what's acting as a force or something affecting the acceleration, we say is going to be negative g. Because of that gravity, there's nothing affecting something horizontally, because in maths, well, at this level, we aren't talking about air resistance in any way. So there's basically no resistance when it comes to horizontal. However, vertical has your gravity resistance. Now, these are the 4 formulas you can assume. You can always start with these and prove the rest from these 4 initial things. All right, so what I'm going to do now is a table on the formulas you need to be able to prove and how to prove them. So let's have a look then, and let's call this table formulas we need to prove. And then I'm going to talk about how to prove them. All right, so we put a line there. The first formula is for horizontal motion. And we're going to prove this. Or more commonly written as. So notice that all this is the integral of one of our initial conditions up here. And you can see that all they've done is chucked a t on the end of it, and now it's x rather than x dot. So this is the position of the particle if you're thinking about displacement, velocity, acceleration. Okay, so how can we prove this? Because we can't just take that assumption. We can't just write that formula without showing how we get it. So to prove it, the big thing you need to do is just to integrate x dot with respect to t. Now remember, it's always going to be respect to t if you are going from x to x dot and x dot dot by differentiating and integrating. Everything is always with respect to t. So I'm just going to write that with respect to t. Okay. All right, so let's think about that. We know that x dot we can assume is v cos alpha. So x is going to be the integral of v cos alpha with respect to t, which is going to give me v cos alpha t. Because remember, this is just going to be some constant, some value that we get as our initial horizontal velocity equation. So it's just going to be some constant. So integrating, we just chuck a t on the end, but don't forget your plus c. Now, your question could differ, but the assumption of our initial conditions at this point is that at time is 0, our position is 0, okay? Which is pretty straightforward. So now saying that, we can see that we're going to have 0 is equal to v cos alpha t plus c. So c, sorry, I'm subbing in 0 here as well. So c is going to be 0, and I'd show these things. So therefore my equation for x is just going to be v, and I'll write it here like this, t cos alpha. And that's the proof to get to this formula. So now we have a formula for the horizontal motion in terms of x and t. Okay, so the idea is with this table is this is going to be telling you how to do it, and then this next part is just showing you. All right, let's go to our next one. So this is where people start to get a bit come undone a little bit, I guess. Thinking about it in the fact, if we're talking about now vertical motion. Our vertical motion is now thinking about your gravity. Okay, we know that horizontal motion had no effect with anything in terms of resistance, but our vertical motion does. So what we can't do this time is we can't just say, oh, well, I know that y dot is equal to v sine alpha. So if we do the same idea, y is just going to be the integral of that. Yeah? No. So put that on your summary here and put a big line through it so you can see and say wrong. Why? Because of gravity. So don't make that mistake. What we have to do, and here's my line of how to do it, we have to integrate y double dot with respect to t. And we know that y double dot is equal to negative g. That was one of our assumed formulas. Okay, so when we do that, we're going to have the integral. So y dot is going to be the integral of negative g with respect to t, which is going to be negative g, because g is our gravity, which is just a number, t plus c. Now, what are our initial conditions to find c? We know that at time is 0, the initial velocity is going to be v sine alpha, one of our assumed formulas. So subbing that in, we get v sine alpha is equal to minus g lots of 0 plus c. So therefore c is equal to v sine alpha. So therefore y dot equals minus gt plus my c, which is v sine alpha. And that there is how we prove this important formula. So that's the formula, and this is the proof to it. So now that is the formula in terms of t at any time for what we could find the vertical velocity at any time. All right, next we want to be able to now find not y dot but y, and it's this formula. Now again, the low students are going to make the mistake and memorize these formulas, but these we can't memorize, we need to be able to prove. So now we can say we can find y by integrating y dot with respect to t. All right. So let's think about that. We need to integrate negative gt plus v sine alpha with respect to t. If I do that, I'm going to get negative gt, add 1 to the power and divide by it, plus vt sine theta, because it's just a constant, so put a t on it, plus c. Now my initial conditions. Think about, what did the question say? And all questions can be different. At time equals 0, where did the particles start? So for instance, if somebody's throwing a ball and this person is 2 meters off the ground, then y would be 2. But if this ball is being projected from the ground, then y is 0. Okay? So let's assume for this particular question, and most of the time it'll be t equals 0 and y equals 0, but if it is different, they will say that in the question. Subbing that in, you're going to get that c is equal to 0. So we can now say, yep, and it is more commonly written in this form, which I've written on the left here. So I'm going to write it in that form and say that vt sine alpha minusing a half gt squared. That's just the more common form to write it, but it doesn't matter if you don't put it in that form and had it in the form above here. Okay, so now we have found an equation for the height of this particle at any time, because it's y in terms of t. One thing we haven't really spent a lot of time looking at so far is finding the equation of this particle in terms of x and y, more commonly known as the Cartesian equation. These are all what we call parametric because they're in terms of t. So what we're going to do is develop a formula for the Cartesian equation of this particle. So a Cartesian equation means we need to eliminate t. And we're going to do that with simultaneous equations. Simult equations. Okay, so I've written what we need to do, and I've written what we need to find. What I'm going to show you is what we're going to get. So this is the proof to how to find this equation. X tan alpha, oops, minus gx squared on 2v lots of 1 plus tan squared alpha. That is the Cartesian equation for the projectile motion of this particle. So if we know the height, the y value, we can find how far away it is, the x value, and vice versa. Alright, once again, we can't memorize this formula, you need to be able to prove it. How can we prove it? Well, it's just about being able to eliminate t with simultaneous equations. So we have, so far, we know this. We just proved it above. So basically, what we need to do is eliminate this t and this t, and we need to replace it with x's. So we think, okay, is there a formula that we know or have proved that has x and t's only in it? Because then we could just rearrange it for t equals and throw it in there so it's all y's and x's. Okay, think back. Yes, there is. We proved just before this formula. In terms of x and t, if I rearrange this, I can write that in the form x over v cos alpha. Okay, so now let's use that. Let's sub it in and see what we get. Pretty ugly, but let's clean it up. We're going to have here, my v's are going to cancel. I'm going to have x sine alpha over cos alpha, and straight away I'm thinking, ding ding ding, that's tan. And I'm going to have minus a half g timesing by x squared over v squared cos squared alpha. Careful to remember that v needs to be squared. And I can clean this up further and think I need to get back to what's on the left here, okay? And I know that obviously we're proving that, so we can't use it, but it's just something good to have there to think, okay, I need to turn it into that, which tells me straight away, turn this into tan. Now, what they've done here, on a little side note, they have replaced cos squared with 1 plus tan squared. The reason they've done that, and the reasoning of how they've done that, is, if I just make a little side note here, this cos value here is really 1 over cos squared alpha, because cos is on the bottom, which is the same thing as sec squared alpha. Now, think about our Pythagorean identity. Sec squared is equal to 1 plus tan squared. So that's all they've done there. They've turned 1 over cos squared alpha into 1 plus tan squared alpha. So now we can replace that and say, okay, I'm going to have minus 1 over 2 g x squared timesing by 1 plus tan squared alpha. And that is me just putting in that substitution here. Okay, and then I can do one more step if I want to and clean it up, and now you'll see that yes, it does turn into that equation. Now, why have they gone to that extra step and eliminated cos for tan? I mean, it hasn't really made it that much nicer, but think it really has, because now we have an equation with both in terms of tan, which just is a nicer form rather than having different sine, cos and tans in one equation. Okay, so that is our Cartesian equation proof. Okay, just think to yourself, to get something into Cartesian form, all you're going to do is eliminate t. How do I eliminate t? I need to put x in instead. So I need to find an equation that has x and t's to make that substitution. Okay, there's two last little formulas that come up, and honestly, they're really just knowing things well. The first one is just being able to find your maximum height. It's really just about being able to do calculus well. The maximum height, think about your particle. Your maximum height. Think, maximum, when have I heard of that? My maximum occurs at my derivative equal to 0. Going back to calculus. So that's all you have to do to find the maximum height. It's the highest value that this projection will get to. So, and to find a maximum, we know we just make the derivative equal to 0. Going back to your stationary points, that's how we would do it. Okay, so what you're going to do is just solve y dot equals 0. You're going to find the time this occurs, because our y dot is in terms of time. Then you're going to sub that in y equals, and that will find you the maximum height in terms of y. Last of all, if you need to find the range, and these are all on the diagrams I first had, think the range of something, the range of our projectile is really just, what's the x-intercept? When does it come back and hit the ground? And how do we do that? We make y 0, because that's how we find an x-intercept. So like I said, these are all, if you know calculus well, you should be able to do this without any kind of help. And to do that, you make y equals 0. Once again, that's going to find you the time this occurs. And to find the actual x value, you sub it into x equals. And that'll give you your x value of your x-intercept. In my next video, I'm going to put all this into a HSC style question and show you how to use these proofs in an exam.